If you're on the other side of your south of you. What is that 24 that goes towards Canton, down towards Canton? So if you're on 24 from Bartonville going towards Canton, it's like 5-10 miles south of Bartonville.
Yeah, I know if you go up the junction or come across the peak and across the bridge on the 24,
Mm-hmm.
you get south.
Mm-hmm. It's not too far out of town. Where is Mapleton?
Yeah. It's better than Maple syrup.
Is that where Mrs. Buttersworth hangs out? Aunt Jemima? All right, folks. Well, today kind of snuck up on me. Today's the last day of class. It is, and it ain't. It is awesome. But we didn't get through a shit ton of material. That's the bad part. So you're gonna have to I'm not, okay. I would encourage you to look through the rest of the chapters. Let's look at, if you noticed on the calendar, you had about 500 homework assignments due today. What I'm gonna do is make it up to you if you want to do those. So chapters 20 through 24. If you did them already, I'm gonna go through your grades. And if they helped your grade, I'm gonna leave it. If they didn't help your grade, I'm gonna make that assignment exempt, so it doesn't hurt your grade. Does that make sense? You will need to know a lot of that material for the final, well, some of it. So here's what I'm gonna do. Did I put that up yet? No, I didn't. What we need to do today is obviously go over what's going to be on the final. So anything that we haven't covered, I'm not going to put that on the final because we haven't covered it. But basically what you missed is everything that we went through in capacitive circuits, right? RC circuits. Then we moved to inductors, and we started to see that the inductive circuits in the homework like they would do today or Tuesday, right? You started to see inductive reactance. Saying what's different about that formula than capacitive reactance? What is the formula for inductive reactance? You remember?
Well, it's 2 times pi times frequency.
2 pi LC. So you remember X sub C, capacitive reactance, was 1 over 2 pi FC. Inductive reactance was, and we'll go through this here in a minute, but it's the same, but it's not the reciprocal. So it equals 2 pi LC, not 1 over, but 2 pi LC. So you can see how capacitive reactance has that inversely proportional deal, where inductive reactance is directly proportional. So I kind of explained this a little bit, but not in detail, but in an RLC circuit, you can use capacitors to counteract the effects of inductors in circuits, and you could use inductors to counteract the effect of capacitors in circuits. And inductors and capacitors are used in all sorts of different ways, for filters, for filtering out sine waves. So take an AC signal and create a DC circuit and vice versa. And then obviously your common inductive loads like transformers and motors. That's why it's important to know the effect that capacitors and inductors have in circuits, okay? Why are you yelling at me?
Like how they work exactly, like how we do with the number,
With the inductors?
with the
I don't know that I have, yeah, maybe. I want to make sure I get through the stuff that we need to know for Tuesday before we run out of time. And I'm gonna go through, remember for your, one of your quizzes, you had to solve an RC circuit with a capacitor. You had to go through step by step and solve. Today, the first thing I'm gonna do is walk through with you how to solve an LC circuit, okay, using those formulas. But keep in mind that I'm going to take that. No, I'm not going to take it off the final. I'm going to leave it on the final, and you're going to have the answers with you if you pay attention in class today. But it's the same. You already know the process. It's just the formulas are a little bit different now because it's inductors rather than capacitors. So what I want you to get out of this class is understanding in general what inductors and capacitors have on circuits, right?
Yeah.
You're not going to be an expert on AC theory when you get your diploma. You're not going to be an expert on any of this stuff. I would hope maybe you are, but I'm not. I'm scratching the surface of all the AC knowledge that's out there, right? So that's why my goal is not to, I don't know. Well, no, I mean, look at you guys. No, my goal as a teacher is you understand the concepts, right? And so far, all of you have grasped that. I know this is a math heavy, not very easy course, but you all have been up to my standards anyway so far. We'll see after the final, but okay, first things first, let's go over. This is where you should probably want to pay attention and write things down because you're going to be given answers that are going to be on the final. Now you will still have to solve an AC or an RC circuit on the final, okay? And we can do an example of that later if you want. But let's do LC because we haven't done this together yet. I just want you to see it. If we would have had more time, if we wouldn't have gotten hit by things like COVID and my day off the other day and all that, we just got way behind, which is okay. Let me get my high-tech software up on the screen here. There's my high-tech software. All right. We're going to create an LC circuit. So I got a 60-volt AC source and it's 6 kilohertz. And I'm going to be working with a resistance of something. Oh, a little better. And then this is the symbol for an inductor. Look familiar to you?
Yeah.
Remember what the transformer looks like? So we're going to have R is 3.95 kilo ohms. And we're going to have L is 150 millihenries. So inductive value capacitors, what was the unit for capacitance? Starts with an F and rhymes with schmerids. Farads. For inductance, starts with an H and rhymes with Schmenry. Henry. So millihenries, 150 millihenries. There is our circuit. So we can solve for E total, I total. What is the total resistance in a AC circuit called? Start with a Z or an I and I is a Schmidt-Stevens, yeah. Voltage across the resistor, current through the resistor, R. Voltage across the inductor, current through the inductor. And what is the resistive value of the inductor? Why are you staring at me? Okay. What's the resistive value of the inductor? What was the resistive value of a capacitor? The ohmic value. Not resistance. What is this? Inductive reactance. Okay, so anything we can put on here right away? R, yep. 3,950 ohms. Anything else? E total, 50 volts. And that's about it. So this is a series RL circuit. Do we have enough information to solve for inductive reactance? Yes, we do. 2 times pi times 150 millihenries. So this would be 0.15 henries. And what's the frequency?
Frequency is
6,000. So I'm getting, what are we getting? Oh. 2 times pi times 0.15 times 6,000 equals. We don't have to do the 1 over, isn't that nice? 5,654.87. Oh, and what's the unit? I almost said it.
Oh, no.
This is the reactance, right? So it's an ohmic value.
I was trying to give the answer, but do it with the wrong.
5,654.87. ohms.
Hey, I'm confused.
Chill out, Lewis.
I know it's the same thing, that's very easy, but the only why else? Maybe just go ahead and just say that way.
It is a resistance. It's resisting current flow in the circuit. And to prove that, anybody familiar with coils, or you're a little familiar with transformers now, right? If I had a circuit, an AC circuit with only an inductor in it, I don't care what the value is. And normally in a circuit, any circuit, we're going to protect the wire with a fuse or breaker, right? That's Joe's department because he works for Eaton. So let's put a fuse in here. This is the symbol for a fuse. It's a really bad one. Let's say this thing cuts off at 1 amp. Protect the wire. An inductor, all it is a wire coiled around and around and around and around and around and around. It comes back out, right? So if I hooked up a straight piece of wire to an AC source, what would the current look like? Because there's not much resistance at all, right? It would be through the roof, and it would blow that fuse. But if I take that same piece of wire and I coil it up a bunch of times, and I put it in that same AC circuit, it has to be AC, it's going to resist current flow, right? It's going to produce a magnetic field, all sorts of good stuff for us. So this is actually, that's why you have an ohmic value there, but it's not resistance, it's inductive reactance. It's resisting current flow in an AC circuit. If I hook that same circuit up to a DC source, that inductor is going to do nothing, right? Because current flow is flowing in one direction. It's not going to resist current flow. If I hook this up to a battery, it's going to blow the fuse. That's what I'm saying.
So that would be the inductor in DC circuit would be more like filter.
It wouldn't do shit. It's just a piece of wire in the circuit. It just happens to be coiled up. In an AC circuit, because it's coiled up, it has inductive reactance. It has to do with the rate of change of current in the circuit. That's where the reactance comes from. Same with a capacitor, right? What?
Is there like little bits of reaction?
Oh yeah, sure. There's minuscule, all this stuff, there's minuscule stuff going on. If you have a purely DC, purely inductive circuit, you would have a little bit of reactance, right? Because you're going from 0 to, let's, if it was 10-volt battery, you're going to from 0 to 10 volts, right? That's a change in current. So for that microsecond, you would have a little bit of reactance on that circuit, but in general, it's negligible.
Like stuff I build, like to use an inductor choke,
Choke, yeah,
and it's in DC, it's after it's been rectified.
for your amps, you mean?
Yeah, so it works kind of like I could put a resistor in place, drop voltage.
Mhm.
So I don't want to get off topic here for our class. So.
Yeah, that's good. And I like to throw these things out there during this stuff so you can see why the hell you're learning it. You know, it doesn't make much sense to me to just, well, here's a bunch of formula, guys, you know, like go have fun with your formulas on your job. You have to understand, and you will see, like for most of you, you will take Electech 150 this summer, right? And in that class, like the trainers that you guys just saw up there, there's a lot of what are called relays and contactors, and they're using magnetic fields created by AC to pull things in and out, right? And all they are is a coil. There's a coil. So you hook that coil up to 120 volts on those trainers, and it will do some work for you. It'll create a magnetic field and pull contacts together. But if I hooked a DC circuit up to that, it would not do anything. It would probably just blow a fuse, you know? And you have to think about what you're actually doing. And I try to explain this in 150, but you're hooking up 120 volts to a piece of wire. Like you would think that would burn up because there would be a bunch of or very little resistance, right? Copper is not very resistant, but you coil it up, it's gonna have this thing called inductive reactance and resist current flow in that circuit. Okay. Back to it. So we got our X sub L inductive reactance. Now, what can we solve for? Schmimpedance? Yes, Schmimpedance. I'm gonna pull up your formula sheet here. What page on your formula sheet should we look at for this? Yep, and there's two of those, so we want X sub L and R in series. So if we're going to solve for total impedance, Z total is the square root of R squared plus X sub L squared. And you get that using this little triangle here because of the phasors. Total impedance here, this diagonal, is found by Pythagorean theorem, where R squared, R is going to be the main one, and X sub L is this one over here. So if we move this phasor and make a triangle out of it and use Pythagorean theorem, we can solve for total impedance, but the formula itself is right here. Whoop. So this is going to be the square root of 3,950 squared plus 5,654 7 squared. So I've already got this number, 564.87 in my calculator. I'm just going to hit squared. Whoop. Plus 3950 squared equals 1.21 gigawatts. And then I square root that. Where are you at? Right there. 6,897.83. What's the units for that? Muy bueno. Did I say that right, Louis? Did I? Did I sound like a freaking gringo when I said it? Okay, all right.
Oh, you like the truth?
Yeah, I want the truth. I'm gonna go cry to my boss. This dude called me a gringo.
Hey, man, I said, don't lie.
You don't lie. What can we solve for now? Co-current, using what law? Ohm's law. I equals E over R. And I total equals E total over Z total equals 60 divided by 6897.83. I'm getting 8 milliamps, 8 point, yeah, 0.008. I'm just gonna write out a bunch of numbers because it'll make my answers more accurate later. 0.8698. Yeah. Now, if the final asked you, what in this circuit, what is the total current in milliamps? What would you put? Correct. Round it to 2 decimal places. Now what can we do? Is it a series circuit?
Yeah, same thing.
Yep. So probably the same lady that told me to put my mask on. So can we use Ohm's law then to solve for voltage across the resistor and voltage across capacitor or the?
Yeah.
Yes. Voltage across the inductor equals total current times inductive reactance. So voltage across the resistor E equals I times R, right? So 0.00869 times 3,950. And voltage across the inductor. 0.008698 times 5,654.87. Anybody do that already? What is the voltage across the resistor? And
Why 5.394?
this,
Yeah,
this E equals I times R, right?
yeah.
So E sub L equals I sub L times X sub L. inductive reactance, right here. That's where that number comes from. E equals I times R, right? It's just Ohm's law.
Okay, that's for,
Right, this is the voltage across the resistor, and this is the voltage across the inductor. So did anybody calculate this one yet?
49.2.
49.20.
Zero, yeah. You have to put zero on there, but,
No,
okay.
if you
I
round.
rounded it. It was,
Yeah.
Yeah. 29 something.
You have just solved for this circuit.
okay. I get the total. Right.
Remember, on the test, you will have this exact question on there. And that's the last time I'm gonna say it.
Will we do parallel as well?
Nope.
So we don't do the individual voltage drop, right? Oh,
Yeah, we did.
34.37 volts in, resistance.
Yep, add those two up, by the way.
Yeah,
34.37 plus 49.20. What is it? 83.57? Way more than 60, isn't it?
yeah.
Total voltage is 60. Why is that? In a series circuit, why couldn't you just add it up? Because of the reactance. So the sine waves are not, the sine waves of those two components are not in phase. They're different, right? If they were in phase, you would get 60 total volts. Because they're out of phase, you don't get, you get individual voltages working together, but they're not, when you add them together, you're not getting the full 83, you're getting 60. Nothing will make them in phase because of the way an inductor reacts in the circuit, right? If you had a resistor in there that was 5,654 ohms of resistance, they would be in phase. The total voltage in that case would be 83,000, whatever, 83 volts. Huh? What? No, no. I mean, it's all about what you're trying to do with the circuit. In this circuit, for some reason, there's a resistor in series with an inductor. Okay. Maybe they're trying to counteract some kind of capacitive something in there. Yeah, this is more for an example of like how an inductor affects a circuit than it is a practical application. What?
How much voltage you say was total?
Well, total volts is 60. That's the source. Okay, we know that. But if you add this and that together, it's way more than 60. And my point was to tell you that's because of inductive reactance. It's because the sine waves are not in phase with each other, right? On your formula sheet, you can kind of see this visually. So voltage across the resistor and voltage across the capacitor right here. The sine waves do not peak at the same time. So if the total voltage is up here, it's not the same as so you have it, ignore the top peak right now. You have voltage across the capacitor, and voltage across the resistor. If those were lined up with each other, which they would only be in a purely resistive circuit, then you could just add those two peaks up, right, for total voltage. But because they're out of phase, the total doesn't end up here, it ends up right here. Right? They're not working perfectly together. They're not working perfectly in sync, if that helps.
This is why you mentioned hands together, right? This is what we use the formula for.
Right. Right. And in this case, 60 volts is just our source. I mean, yeah, you don't have any choice there. But if you had two resistors in a circuit and you did all those calculations using Ohm's law, and you added the two total voltages up, they would equal the total voltage. All right. I'm creating a test for you. Called final exam practice. I'm going to put in there all of these questions. I'm going to allow you an unlimited number of attempts. There's no due date. This will not affect your grade. What?
If we don't pass it, we get a name.
Here it is, final exam practice. So on your final next Tuesday, you're gonna have 24 multiple choice questions that will be pulled straight from these examples. Ready? Thank you, Zach.
Thank you.
So you can do this as many times as you need to, okay? It will not affect your grade. 24 multiple choice questions.
I'm not sure if your students today got a good idea, and they'll have to find the next Tuesday. We don't have class Thursday then?
No, you're done, dude. You're done after the final.
Oh.
On like a freight train.
We can still do the rest of the homework.
Yes, I would encourage you to. Okay, and I apologize that I didn't squeeze it all in.
How long we have to take for doing the rest of the homework?
Let's make that by 9 a.m. on by 9 a.m. on Tuesday. We'll take it the final Tuesday at 9 a.m. If you're going to do any more homework, please do it before then so that I can go through all of those and exempt the ones that hurt your grade,
Okay.
okay?
Can you give me a copy of that?
Of what? Can I print you a copy of that? No,
No, this is take it home.
no, I cannot. But this will be on,
No, you got copy?
no, I cannot, but this will be on YouTube later, if you want to go back through how we solved that.
Okay.
Did everybody see where to get to that final exam practice?
Yeah.
Okay. Next. Everybody done with all this? Okay. We're gonna go back to RC circuits and we're gonna do a series one. Because we went over this, I expect you to know it, so I'm not gonna give you all the answers, but we'll do an example, okay? So I'm gonna call this 50 volts. I'm gonna say it's 35 kilohertz. I'm gonna say this is 3.2 kilo ohms. I'm gonna say this is 1 microfarad. So, Wilson. Can we solve for this whole freaking thing?
Yeah.
Yeah, let's do it. E total, I total, Z total, ER, IR, R, E, C, I, C. What can we put in there right away? E total. Anything else? 3,200 ohms. Now what can we do? What's the formula?
1 divided by 2.5.
2 pi got C. 1 divided by 2 times pi times 35,000 0.001. Microfarads for 1 microfarad. What if that said 900 nanofarads? Could you do it? Nano would be 9. Right. Nano is 9. Pico is 12. Right. 1 divided by left parentheses 2 times I 35,000 times 0.000001. Right parentheses equals 4.5 ohms. That can't be right. Oh, that's why. I need to change this so it makes more sense. I'm gonna change this to nanofarads. I'm changing it to nanofarads. Yeah. If that's the case, it's 1 divided by 2 times pi times 35,000 times. Yeah, 1 nanofarad would be 0.000000001, right? Could we have solved it the first way I did it? Yes, but that makes the capacitive reactance, the resistance value in the circuit so freaking small compared to the other one, you're not getting anything out of it. So, and this more closely will resemble what you see on the final two. So bear with me. All right, so 1 divided by left parentheses 2 times pi times 35,000 times 0.000000001. Right parentheses equals, that's better. Now we got 3.2 k ohms, no resistance, and we got capacitive reactance of 4.5 k ohms. Following me or no? So make sure I'm not making it too confusing, but I want it to resemble what you're going to see on the final. Or piece of shit, excuse me.
44, 4.5, 47.
4,547.28 ohms. Now what can we do? Schmimpedance. You guys want to hear my Nazi joke? Knock, knock. Viva ask the questions. It works a lot better if you smack the person before you say the punchline, but I can't hit my students. What am I doing? Oh. RC series. Total impedance. Square root of resistance squared plus x sub c squared. Right? Found it. Which equals square root of 35,000 squared plus 4,000 35,000. Where am I getting 35,000? Frequency, dumbass. R squared would be 3,200 squared. Right? 4,547.28 squared. I'm getting 5560. Is that what everybody else is getting? 0.37. I just put this into my calculator. How did I get what? Which part? How did I punch in the calculator, or how did I? Yeah, this is on the computer calculator, but I don't have one of yours in front of me. But if I do 3,200 squared plus 4,547.28 squared equals, and then hit the square root button, I get 5560.73.
Oh, I got it. I must have.
Okay, now what can we do? What? You're lost? On which part?
Formula. Because I got 3,200.
So this is our formula, right? The square root of r squared plus x sub c squared. So I put a square root here, and then 3,200 squared, that's r squared,
Okay.
plus x sub c squared. What is x sub c?
For
4,547.28 ohms.
what?
Squared.
Okay. Good. Put it up, right?
Throw me your
I
calculator.
know what the problem was.
You got it?
Yeah.
Okay.
What, 4,000 something? 547? I put that, 4.547 or 28, we're going to be from
Okay. So did you end up with 5,560 ohms?
Yeah.
Okay, good.
when I did away the 5.5.
Moving on. So now what can we solve for? Yep, I total. Equals E total over Z total. Equals 50 divided by 5,560.37. I'm getting 8 basically 9 milliamps. 899. Series circuit, right? So I total equals IR equals IC. Oop. Oop. Now can we use Ohm's law to solve for the voltage across the resistor and the voltage across the capacitor? Sure enough. .78 volts. And 40.88. Well, congratulations, guys. You just solved for a series RC circuit. Everybody good?
So the only difference between curious is what the recipients and the whole control of this the formula, right? The way the what the work with the different voltages.
Yeah, so you're talking about RC series versus RC
Yeah.
parallel. The only difference is how you solve it, like, right?
So,
Because in this circuit, the current stayed the same, right?
mhm.
And on a parallel circuit, the voltage stays the same, right?
And that's where, capacitance and correct, capacitor resistance and, inductor resistance. It's do the same thing too, only difference is, the formula is both, the, here, right?
Ask that again.
For, capacitor resistance, the only difference is the formula solve the inductor resistance and capacitor resistance, they are different, but besides that.
Oh, yeah, and then in an inductive circuit, the one we did before, yeah, it's just the formula is different. Instead of 1 over all that stuff, it's just 2 pi LC for inductive reactance.
And the other thing that we're talking is about different, you know. Yeah, I think in a way I have a problem just fine with the field. These are numbers, and one of the numbers is like, I still try to think how to fix this. So like 4,000, 4.5, 147, and it's up to and the calculator 4.47, 528, it's gonna be that number. For, 147, point 547.28, instead of 4,547.28, this is the number.
Corey?
Rough, I got put this one at no point. Not gonna affect the final.
No, there's a tolerance. So if you run into that when you're all done and you see, say, hey, I think I did this right, then just tell me and I'll correct it.
Okay.
All right, onward and upward. I'm going from hard to easy. So the further we go, the easier these will be. But in an AC circuit, 40 volts AC. And let's do three inductors at a circuit series. Let's say this inductor has a reactance of 200 ohms. This inductor about 1. Woo! This inductor has a reactance of 120 ohms. This inductor has a reactance of 190 ohms. What would your total inductive reactance. B.
This direction.
Yep. We haven't covered this, but I want you to just think about it.
Wow. And then together.
Huh?
We end them together.
Are they ohmic values?
Yeah, wow.
Yes, they are. So yep, you just add them together.
What's the difference? 200 on, taking 120 to 200.
200, 120, and 190.
What do you-
What's the total current in this circuit?
What's the total current in this? Yeah.
Mhm. Total divided by X sub L total. 40 divided by 510.
Seventy-eight, 143 million.
78.43 million.
Don't believe me.
Why it does
Somebody
that?
will do it.
And if I picked one of these inductors, like let's say the voltage across L3, inductor number 3, using Ohm's law, E equals I times R, right?
Yeah.
So it'd be the current of L3 times X sub L3, right? Is the current in L3 the same as it is the rest of the circuit?
Yeah.
Yep. So 0.07843 times 190. Right?
Yeah.
Everybody get that?
14.9.
14.9. Everybody done with this page? Can we move on? Transformer time. Um, 100 volts. AC, 50 hertz. There's an 8, a 1 step down transformer. And we're going to say this is 6 ohms. So E primary, I primary, power in the primary. Okay, let's solve for all this stuff. Anything we can put down right away? Anything else? Primary voltage? What does that mean our secondary voltage is?
Oh, it's a 8 to 1, right?
8 to
So
1
it's
step
divided
down. So it'd be 100 divided by 8. What did you say it was?
12.5.
12.5 volts. What is our secondary current?
Well, 12.5, right?
2.08 amps. What's our power in the secondary? What's the formula? Big old slice of V equals I times E. .08 times 12.5. I'm getting 26.04. What's the unit for power? Watts. Now what can we do?
You got 26.4?
26.04 watts. 2.08 times, oh, I didn't do that right today.
I got 26, I don't know, I'll make the band.
2.08 times, I probably divided by, oh, wait, yeah, that's right. 2.08 times 12.5.
You got 26, right? Oh, you got 26 is why I asked.
Yeah.
I don't have the 24.
Oh, I didn't round the, mine was 2.0833333333.
Oh, what is that?
Either way, you should do well. Yeah. So what's our rule?
I was checking about.
These are always the same, right? 26.04 watts. So what's the current in the primary? IP equals EP. Oh. P equals I times E, so I equals P over E. Ooh, 26.04 divided by 100. So 2000, 0.20, 260 million. Everybody good on the transformer stuff? All right. What's the formula for period? Remember that? Is it on your formula sheet? If not, you should write it on there. Pretty easy one. That's time constant.
What's the formula? What was the repeat?
Has to do with frequency, remember?
Yeah.
1 over F. So if I told you a sine wave had 800 hertz, what would the period be in milliseconds? Well, how do you solve for it? 1 divided by 800, right? $1.25 million milliseconds. What if I told you a sine wave had a frequency What if I told you the period was 500 microseconds? What would the frequency be in kilohertz? If T is 1 over F, what does F equal? 1 over T, right? If T equals 1 over F, F equals 1 over T. Do I need to go through that algebra with you? I hope not. So if F is 1 over T, 1 over 0.0005 makes the frequency equal 2000. So if the question asks for what's the frequency in kilohertz, 2. Good. All right. Sine wave. Remember RMS versus peak? What is the red dotted line represent? RMS. Which means that this distance is peak. This distance is RMS. And this distance is what? Peak to peak. I don't know if you have formulas for this on your sheet or not, but let's just put them on there. VRMS is what percentage of the peak value? 0.707. Remember that? V peak to peak is V peak times 2. Pretty simple, right? So the question said, I got a peak to peak value of 83.5 volts. And I want to know what VRMS is. The VRMS is going to be 0.707 times something, right? What is V peak? It's half of 83.5, right? This is the example we're given.
Oh,
We're
yeah.
trying to find this.
Yeah.
So if 0.707 times V peak is VRMS, it'd be 83.5 divided by 2, right? So what are you getting for an RMS value? 41.75. That's V peak. Right? That's 83.5 divided by 2. So you just solved for V peak, but we want to know what VRMS is. We still have to multiply that times 0.707, right? So what's VRMS? 29.52 volts. Okay. Good. What if I asked you, I've got a sine wave of 110 volts RMS. What is the peak? Using this formula, the V peak is times 0.707 is VRMS. If you solve for V peak by dividing 0.707 on both sides, you get VRMS divided by 0.707. Correct? So what does that give us?
5.54.
One,
I multiplied that off by 1.414.
yeah, either way you want to do it is fine. I'm minimizing the amount of formulas that you guys need, so if you're more comfortable with that, that's fine. What was it though, 155 point what?
54. Say 5.4, is that 5.9?
155.5.
1.4.
You think it's a formula, but same shit.
Yeah.
Same thing.
Yeah, it comes out 5.9 if you do this.
Yeah, fine.
What?
One ten, and
1.4.
All right, what is the formula for capacitive reactance?
1 divided by 2.5.
Um, and if I asked you to solve for capacitance, if I gave you a reactance and a frequency, could you solve for capacitance? You're mixing capacitance and inductance. I'm just saying, with this formula, if I switch things around and needed to solve for capacitance, could you do it?
or you switch, SC for S.
Right? What if I wanted to solve for frequency? If I gave you capacitive reactance and capacitance?
1.25.
Right? You're switching those two. Just algebra, right? But there might be a question on there that says, hey, here's a frequency of this, and here's a capacitance of this. What is a capacitive reactance? You're going to use this formula, right? There might be a question on there that says, there's a capacitive reactance of this and a capacitance of this. You're going to use, and I want you to find the frequency. You use that formula, right? You can have these formulas on your formula sheet if you want to write them down. Okay. Beyond everything that we've just gone over, there are a couple questions that deal with if I have this many capacitors in series, what is total capacitance? If there's this many capacitors in parallel with. I've just made those extra credit. Okay? No. Just kidding.
I just got a text saying my landlord had a heart attack, so I totally missed it.
Screw your landlord. No, I'm just
Yeah, I
kidding.
went to pay my rent this month. Laughing there.
Lord,
Anyway, I'm just admitting that I wasn't listening
basically what I'm trying to say is everything that we've gone over so far is what you need to know for the final. There are a couple more questions that deal with, old stuff that I don't really care if you know or not, so they're extra credit. Like parallel capacitances and series capacitances and phase angle. You have enough knowledge in you to do them, but what we've gone over so far is a lot of math, you know. So to me,
So capacitance and,
What?
Capacitance, they work the same way in
just remember that
they work like.
if it's an ohmic value,
They work the same.
it works just like a resistor. If it's not, it's the opposite, right? That reciprocal formula. But again, those, I would save those for last because they're gonna be extra credit questions. All right, so that concludes your final exam review. Now we need to look at, before you go, all the labs that we didn't get to. Who has labs that they still need to turn in?
When we started last week, 17, we finished.
Yeah, we don't really have time to finish it.
Mhm.
So. I'll just do the 17A will not be for a grade. You guys are welcome to work on them if you want, but I don't want you to turn them in. Just one more thing that I have to grade. If you want to do them on your own time with the lab equipment, you're welcome to. Yes, please. If you don't have any of the other labs submitted yet, make sure you get them into me so I can give you a grade for them. Okey doke. All right, who's excited to take the final next Tuesday? Whoop, whoop. I am. Good thing is you got all the formulas you need right in front of you. And there's no more homework assignments. I mean, unless you want to. Everybody good? Everybody happy? Need to go over anything else? My brain hurts. I don't know about you guys. You need to smokerize it? What'd you say?
The manufacturer smoker, right?
I'm still telling on you for calling me that bad name earlier.
Yeah.
All right, and also, once the video of everything we just did, once that processes, I will, I'll put that up on the shared drive. If you guys want to go over it this weekend or whatever.